Hi, everyone. My name is Joe Xiao, and I'm a Master's of Computer Science student at UIUC. I'm working towards the degree part-time. My full-time job is lead AI scientist at Target. And today I'd like to talk to you a little bit about this cool technology called word embeddings, and it relates to how Target and other large companies recommend their products. So, so here's the kind of the topic we'd like to discuss here. Um, Before we do that, I'd like to just give a quick demo about what I'm talking about. So recommender systems are a way for companies to recommend products. So for example, if I go to the Target website and I look at my favorite laptop, the Dell XPS, um, we can see that I will get other product recommendations, essentially other laptops and also accessories. So how does the system know what to recommend? And this goes back to our topic for today, which is embeddings, but really it starts with word embeddings, which is a sub sort of field, um, sub area, I guess, in the field of natural language processing. So yeah, so I like to talk about word embeddings and kind of lead that into recommender systems. So okay, trying to find my notes here. Okay, yeah, so word embeddings. For example, if we want to look at, two words, say apple and oranges or orange, out of, a whole corpus or vocabulary of, say, tens or hundreds of words, how may we do that? Um, One way is to represent each word in the vocabulary as a element in a vector. So essentially, we can represent, apple as a vector of size, let's say 10 to the 5, where every position is 0 except for where the word apple appears. Similarly, for orange, we can do that as well. Maybe orange is here, and then everything else um, are zeros. So this is something called one-hot encoding. Essentially, the one-hot is the place where we actually have our vocabulary or our word. And you can represent words this way. But now here's an issue. The issue is this representation is sparse, meaning that you know you get a lot of empty spaces with zeros, and really the only useful information is where the words are. So every vector of 10 to the fifth in length, you get really one kind of piece of information. So that's not really good for computation. Um, and the other thing is that if we try to measure similarity between words, we're going to find that uh, you know all words are equal distant, um, because of this one hot encoding scheme. They're all every word, every pair of words are going to have the same distance. So that's really not very useful if we want to. What we want instead um, is a representation. So what we want is a representation that's dense, meaning that information is condensed, is concise. There isn't a lot of useless information in the representation, and we want similar words to basically have smaller distances between them if we're representing them, as vectors in this vector representation. So that's kind of the goal that we want. And this is where this concept of word embedding comes in. And specifically today, we're going to talk about this algorithm called word-to-vec, which is very popular. And we're going to talk about essentially this something called continuous bag of words version or flavor of this algorithm. It's very similar to another flavor, but so we'll just go with this. So the idea is this: if we have a whole vocabulary, let's say it's only 5 words, right? So let's say that it's hope and set you free. So let's say our whole vocabulary is only 5 words. The idea is that if you're given some context words, like say hope and set, so these are context words, can we predict the center word? So can we predict can? And if we can do that, then we can have a way to represent these words and represent them in a way that that we find useful. So how can we do this? So this is how the algorithm works, and it's actually, word-to-vec here is actually a deep learning algorithm. So deep learning, deep neural networks. Deep neural networks. So this is a deep learning application. So what do we do here? So suppose I'm just gonna say copy over, this thing here and bring that over here. So we have this, and we want to represent. We have access to the context words, and we want to predict the center word. So what we can do is represent the context words, let's say hope, or set as first as one hot vector. So hope is the first element has information. Set is the third element has information. And so these are, vectors of dimension 5 by 1. We want to encode them into and so we can, if you're familiar with deep learning or deep neural networks, we can consider kind of each element in a vector as input to a neuron, which is sort of represented by these circles here. And we want to encode them into a vector of, let's say, 3 by 1. So we can consider that a layer, neuron layer of with 3 neurons. And how do we represent that? Well, how do we do the encoding? We can learn these weights. And the weights are really just the connections between neurons. So, this is the connections to the first neuron. These are connections to the second neuron, and so on. So we can learn these weights. So this weight vector now is going to be of dimension 3 by 5. And then what we're going to get is we're going to get something called this is the embedding vector. So this is actually how we would like to represent these words instead of the one hot representation. So we'll call these embedding vectors, maybe we'll call them E. And then what's going to happen is we're going to turn this embedding vector into back into a 5x1 vector. And this is something called a softmax layer. Essentially, we use the transpose of this W here, which is going to be a 5x3 matrix. And this softmax result is going to be really 5 probabilities, each one representing the probability of the word, of a word in the vocabulary. In this case, we have 5 words here. And so this is going to be, since these are probabilities, they're going to sum up to 1. And you know, in terms of how this softmax is done, it's you know, the probability, ith probability is going to be e to the w. What was it? It's going to be like basically the weights to the first neuron here. I just say it's wi times that embedding vector, and then we're gonna sum over all of the embedding vectors. So the detail is not so important here. It's really that we want to turn it into a vector of probabilities. And then now, so this is something, this is essentially the output. So this is the output. And we want to compare this to the ground truth, which is the word will. Remember that the center word between hope, sorry, it's not will, it's can. Hope can set you free. So the center word is can, and that has a one hot representation like this. Yeah. So, okay, so now we have the output, we have the so-called ground truth, and then we can compute something called, we can essentially compute the error, or it's also called the loss, which is the ground truth minus the output, which is a vector of probabilities. Now, this error is going to be, let's just say, the error or the loss, let's just call this a loss vector. So this loss is going to help us adjust, you know, these weights in this neural network. And eventually we want to adjust the weights so that the output and the ground truth becomes very similar. And that's when we know the neural network is working as intended. And that's when we can trust this embedding and actually use it. So how do we adjust these weights? We use the loss. Essentially, this is a process called backpropagation, and or backprop for short. And so those that are familiar with deep learning, this should be very familiar to you. But essentially what we want to do is for every weight, let's say Wi in the neural network, we want to adjust it in the following way. We want it to essentially we want it to follow the gradient, and the gradient is the loss, is the partial derivative of the loss with respect to that weight, Wi. And this is the way, so we do this in a lot of iterations using using the context words. And what we also do is we move, so if I copy this, oops, if I copy this over again, we can move the data around, meaning, when we do our first training, maybe these are the context words and we have like a window like this, but then we can move this window. We can say, okay, now these two are the context words and now this is the center word. And then we can move that again. And then now this is the center word. So imagine if you have a very large vocabulary, then you can keep doing this and get a lot of training data. And the training data in each iteration, you would compute a loss and then use that to adjust the weights. So after a lot of training, then your weights will be adjusted, and we can then use this embedding vector E here. So this becomes the embedding vector is what we're going to use to embed our words in the vocabulary. And again, this will have the benefit of dense representation, as well as the ability to represent similar words with, have smaller vector distances between them. So why does this matter? If we think back to our recommender system, recommender algorithms, we can use a very similar method to represent items now in a similar manner. So we can embed items into vectors, and this uses the concept of items, words. We can kind of abstract items like we do words, and items can kind of, your whole collection of all the items that you sell is like the vocabulary of all the words. And once we can embed items into vectors, then we can start to, we can, given some item, 1, which might have a, let's just say in 2D, a vector representation like this, then we can find, an item 2 that's close to it. And how we measure, closeness or similarity is through the vector difference or the distance between vectors. And so, we can then say, okay, well, we have, say items 2 and 3, then, this distance D 1, 3 versus this distance D 1, 2. We can see that, this distance D1, 2 is definitely smaller, and therefore this item 2 is what we want to recommend because it's similar in terms of content. So this is a class of recommendation algorithms called, content-based recommendations. Of course, there are a lot. there are more sophisticated techniques. There are techniques that involve other users known as collaborative filtering. So I would say content-based recommendation is a more straightforward kind of method, but it's still very popular, and it makes use of this idea of embeddings, which stemmed from embedding of words. Yeah, so this is a topic that I wanted to share today. Hope you enjoyed it, and thank you for your attention.